Okay, we're going to look at another integral of evaluating a double integral over a two-dimensional region in rectangular coordinates. Okay, so we have a function here. This function's continuous everywhere, so that's good news. We've got a region that is closed and bounded, so this integral is defined based on the definition of the definite integral. And then we want to think about using Fubini's theorem, so function needs to be continuous everywhere. It is, or at least on our region it is. And then we want to think about our region being x simple, y simple, neither, or both. Okay, so let's think about going through this region in the direction of increasing x. So if I go through this region, you want to make sure you're thinking about the whole region and not just a part of it. I'm always entering at x equals 0, and then I'm always leaving through this slanted line here. So this region is x simple. And then if I want to think about this region as y simple, go through the region in the direction of increasing y. And you can see that I'm always entering along the slanty line. I'm leaving along this horizontal line at the top. So this region is also y simple. So this region is both. So that means in terms of the region, I can set my integral up with either dx or dy on the inner integral. All right, when you look at this function, however, and you think about integrating this function with respect to x or y, if your integration skills are good from Calc 1 and 2, or what we reviewed earlier in this semester, you should have some concerns about trying to integrate this with respect to y. You would really prefer to integrate this with respect to x. I'm going to go ahead and set this up both ways, and then we'll talk a little bit more about that, integrating with respect to y, why that's a problem. That tends to be a thing sometimes students have forgotten. But when we actually evaluate the integral, we'll want to do that with dx on the inner integral. Okay, so if I set this up in terms of thinking of an x simple region with dx on the inner integral, again, I always write down my outer integration sign first and then go back and fill in those limits of integration. Our inner integral is going to be where we're going to have our x limits of integration, dx on the inner integral, and then dy on the outer integral. So when I think about going through this region in the direction of increasing x, when I enter this region, I'm always entering at x equals 0. I'm going to go ahead and write x equals here, just to remind you, but you could just write 0 there. Dx tells us that that's an x value. And then I'm leaving through this line. So again, either you're given the equation of that line or you write the equation of that line. That's basic algebra. Y equals mx plus b. Slope is 2. Y-intercept is 0. So the equation of that line is y equals 2x. If I'm doing dx on the inner integral, though, I need that in terms of x. So I'll solve for x. X equals y over 2. And then when I set up my outer limits of integration, once I've set it up in the x direction, I want to collapse back in the x direction and look at that shadow of that region. We're going to just be here on the y-axis from y equals 0 to 2. My marker's not cooperating here. Y equals 0 to 2. Okay, so that's the one we'll actually end up evaluating. I'm going to go ahead and set it up with dy on the inner integral just to make sure we can think about how to think about that. Setting it up, you can set it up. It's the integration that's a problem. All right, so my inner limits of integration are going to be in terms of y. So I'm going to think about when I go through this region in the direction of increasing y, I'm entering along this slanted line, so y equals 2x. And then I'm going to leave through this top line, which is y equals 2. And then my dx, my outer limits of integration. So I want to think about once I go through that region in the y direction, I want to collapse that back in the y direction, collapse that onto the remaining variable. And so that'll give us the shadow region down here on the x-axis. X will go from 0 to 1. Okay, so this is not the one we're going to do, but I want to just talk about a little bit to make sure that we're clear about that. The integral of e to the y squared with respect to y is a non-elementary integral. You talked about those in Calc 2. So essentially what that means is that you're not going to write down an antiderivative for this function. No matter how hard you try, you're not going to write down an antiderivative for e to the y squared that is just some combination of e's and y's and maybe powers of y's or whatever. You're not going to be able to do that. So this is a non-elementary integral with respect to y. When you did do integrals like this, had to do with the series chapter that you did in Calc 2. It is possible that you might be able to write a Taylor series that converges to this function and then integrate the Taylor series with respect to y, evaluate the Taylor series from 2x to 2, and then integrate again. So maybe you could do this, but it's going to require Taylor series to do this problem. And probably you would like to avoid that, not only Taylor series once, but dealing with it really twice, because you've got 2 layers of integration here. So if you are not comfortable recognizing this as a non-elementary integral, that might be something that you want to review from chapter 10 in our textbook, which is where you did the Taylor series for non-elementary integrals. In general, though, if you're trying to do some really crazy integration methods that are very complicated for this class, you're probably going about the problem in the most difficult possible way. Many of the problems have a much easier way to go through the problem. This is much simpler to integrate with respect to x. So that's just a warning. If you're just filling up pages and pages and pages with integration, you've probably chosen a difficult path through the problem, and you should probably go back and reevaluate how you started at the very beginning. All right, so here I want to integrate with respect to x. This integral is actually very simple because when I integrate with respect to x, I'm treating all the other variables as constants. So this is all treated as a constant. So I'm just integrating a constant with respect to x. I will just get the constant times x. So my outer integral here, I'll still have y going from 0 to 2. When I integrate this function with respect to x, I'll have x e to the y squared. And that's going to be evaluated from x equals 0 to y over 2 dy. Okay, plugging in my limits of integration. So I found my antiderivative. I'm now using fundamental theorem of calculus with those limits of integration here. So I plug in my upper limit of integration. So I'll have y over 2 times e to the y squared. Remember, those are going in for x. And then I'll have minus 0 e to the y squared. So I don't even really need to write that part. Okay, so now I'm going to have to finish this by integrating with respect to y. And I still have an e to the y squared here. But you should notice that I actually have something that appeared after that first integration that made this a much easier problem to do. This is an antiderivative that you can find via u substitution. I have this extra y out here, which helps with the u substitution. So I'm going to go ahead and write out that u substitution since I know it might have been a while since you did too much of that. If you can do the u substitution in your head, that's okay. All right, so I would let u equal y squared. Du would be 2y dy. I don't have 2y dy here. I just have y dy. So I need to adjust for this constant. There are different ways you can handle that. I would probably choose to divide through by 2. So 1/2 du is y dy. And because I have a definite integral here, y going from 0 to 2, there are 2 ways that you can handle those limits of integration. If you write this down as a du integral, then these limits of integration really should be converted to u values. I often prefer not to do that, and so I do something with my notation that allows me to do that. Either way is okay, though. I want to talk about what you need to not write, though. Okay, so in place of the y dy, I'm going to put 1/2 du. I've already got a 1/2 in here, so I'll have a 1/2 times 1/2. Or 1/4. In place of the y dy, I'll put 1/2 du. And then in place of the y squared, I'll put u. So I have 1/4 e to the u du. What I cannot do is just write limits of integration going from 0 to 2, because with this notation, that would indicate these are u values, and those are not. So I can either use my u substitution to convert those to u values. When y equals 0, u equals 0, but when y equals 2, u equals 4. That's probably how you did it in Calculus 1 and maybe even in Calculus 2. If you only have numbers for your limits of integration, that's perfectly fine, and I don't care if you do that. What I have written here is not quite right, though. So I either need to convert these to be u values, or what I often do is I just put a label here that indicates that these are not u values, that these are y values, y equals 0 to y equals 2. So you need something, either y values to indicate that they are not this letter, or convert them so that they are that letter. Or do the u substitution in your head. That's okay too. All right, so when I go ahead and do this integration, I'll have 1/4. And then the integral of e to the u is e to the u. I'm going to go ahead and back substitute for my u. So I'll have e to the y squared, and y goes from 0 to 2 here. So this is my y. All right, so we'll put these limits of integration in. 1/4 e to the 4th minus 1/4 e to the 0. E to the 0 is just 1, so this last term here is just 1/4. So you could leave it like this. I'm going to go ahead. Our textbook likes to factor out coefficients. So 1/4 e to the 4th minus 1, the whole quantity there. Okay, so again, if you're doing pages and pages of integration or really difficult integration, you probably should have chosen an easier way through the problem. I would say u substitution is a reasonable integration technique you should be able to do, but parts, also some of the other integration techniques, though, that are pretty complicated, you should not be having to do in any of the homework that I have assigned for this class. All right, we'll look at another example in the next video.